So welcome to another video, and in this video we're going to talk about the reactions of ethers. Specifically, I'm going to go over the mechanisms. In a couple of videos then we're just going to do just pure organic synthesis and just predicting products rather than the mechanisms. So in general, ethers do not react in base. So do not react in, especially strong bases. Do not react with base. All right. Ethers prefer acidic conditions. Remember we said ether is some sort of R group with the O sandwich in the middle. So let's look at a couple problems. Let's look at a couple mechanisms here. So I have this ether here, right? And I'm going to add HBr. Again, HBr is an acidic condition. Now, my oxygen has 2 lone pairs on it. So my oxygen is actually going to serve as my nucleophile here. So the lone pairs are going to attack the hydrogen, break this bond between the hydrogen and the bromine, right? And this is what you get. You get an oxygen that has a +1 formal charge. Now remember, in this step, we also kicked off the bromine. Our bromine has a negative charge. So remember this for me. In acidic conditions, ethers, your nucleophile will attack the more substituted carbon. In this case, however, you can see that we have perfect symmetry. So it doesn't matter in this case. So my bromine anion is going to attack the carbon and then kicks off the electrons on the oxygen, right? So doing that, we get this. We get an alcohol plus a bromine. So we get, these are the 2 products that we get. Now the reaction doesn't stop there, right? Because remember, we have plenty of HBr molecules in solution, right? So the reaction doesn't stop there, right? So this oxygen on this alcohol that we just made is going to actually attack the hydrogen and kick off the bromine again. This will produce an oxygen that has a positive charge. All right, and plus we still have this bromine product here in solution. All right. So then the bromine that becomes negatively charged comes in, attacks my carbon, and kick off water as a leaving group. So my net products will be, let me see where I could write this. My net products here would be which is what we had at first here. So these would be your meth products or net products here. So that's just the general, mechanisms for ethers. Pretty simple. Let's look at another one. This one includes ring opening. So maybe we have this 5-membered ring here, right? And we react this in HI. Now, typically you'll see HCl and HBr, hydrobromic acid. Iodine is pretty expensive, so that's just a side note. But to keep the video going, right? Again, my oxygen is going to serve as my nucleophile. So these electrons comes, take all that hydrogen, kicks that off on the bromine, and here's what happens. All right, my oxygen gets a +1 formal charge. Yes, 3 bonds, 2 lone pairs, 1 lone pair. Right, so oxygen gets a negative formal charge, a +1 formal charge. Now my iodide is actually negatively charged now since it gained 2 electrons. Right, so this is going to attack the most substituted carbon. Again, this is very symmetric, so it doesn't matter in this case. So attacks my carbon and kicks off, break those bonds between the oxygen and carbon to give me an alcohol. So this is the part where with ring openings, you got to count your carbons. If you don't, you're going to make mistakes. So counting our carbons, let's see how many members is in the ring. So I have 1, 2, 3, 4, 5, which is going to be my iodide. So, all right, so we have a 5-membered ring here. So the ring is going to open. So on number 1, I have an alcohol, right? That's bonded to this carbon, which is bonded to this carbon, which is bonded to this carbon, yes, which is bonded to this carbon, right? which is bonded to this carbon, right? But this carbon also have an iodide on the end here. Yeah. So let's see, we have 1, 2, 3, 4, 5. All right, so we have 5. So even I miscounted my carbon. 2, 3, 4, 5. All right, so we have a 5-membered ring with an iodide bonded to it, right? So again, 5-membered ring, but we have this extra iodide that's bonded to it. So this is what we get. So let me redraw this product here. All right. And again, in solution, this oxygen won't stay won't stay forever. Again, so we add more HI, which is just in solution. Oxygen gets protonation, take all these hydrogen, break this bond between the iodide and the oxygen and the hydrogen, right? And then we get water. 1, 2, 3, 4. And then we have this iodide here. Yeah. My water has a +1 formal charge. So now the iodide that gains this negative charge is going to come and attack my carbon that's contained in my leaving group and kicks off water. All right. So my product would be this iodide bonded to this carbon, this carbon, this carbon, this carbon, this carbon. So this will be my product here. All right. So again, it's very important to count your carbons. Again, we have a 5-membered ring here with an iodide that's bonded to the last carbon, which will be in total a carbon chain of 6. So that's the ring opening of the ethers. All right. Now let's look at a special case here. Let's look at a very special case here. So remember we said that when we form alcohols in these mechanisms, right? Whenever we form alcohols in these mechanisms, they actually don't stay around for long. They gain protonation again to give you that net product of those alkyl, halides, right? Well, let's see what happens here. Well, again, mechanism says my oxygen is going to come and take my hydrogen. It's going to kick off on the bromine, right? So I'm going to get an ether. I'm going to get an oxygen that has a positive charge. I'm just going to draw my benzene ring as this. It's just way much more easier than this, but they're the same. They're very equivalent, right? So again, my oxygen has a +1 formal charge. Right, has a hydrogen, so it has a +1 formal charge. All right, so I'm trying to get this to focus, guys. So give me a second here. Boom. All right, so now that I have my oxygen that has a +1 formal charge, remember we kicked off bromine in solution, right? That's negatively charged. So this is ready to attack. Now this, we said that in acidic solutions or nucleophile attacks are more substituted carbon. Well, again, we haven't learned anything about adding, substituents to the benzene ring yet. So we know this is the only option to go. So my bromine is going to attack my carbon and it's going to break that bond to give me actually now this molecule. I have an alcohol plus, again, I have a bromine that's bonded to this carbon, that's bonded to this carbon, right? So we have a bromine that's bonded to this carbon, that's bonded to that carbon, all right? So again, let's see, we have a bromine that's bonded here, bonded to bromine, so yeah. So this should be the products, and it's kind of a pain in the butt to count your carbons, guys, but again, it is what it is, all right? So here's the deal. The reaction actually stops here. This is actually phenol. And phenol is actually really stable. So this is the very rare exception where this oxygen doesn't go ahead and get protonated again. All right. So just remember this from your reaction here. Anytime you see phenol as a product, your reaction stops there. So this will not get protonated. All right. So that being said, let's look at another one. All right, so let's see here. Kind of really, these problems are kind of all over the place. But let's see here. If we added this molecule here. All right, so what if we added this molecule here? This is actually called anisole. So you will have to remember this. All right, and we take anisole and we add HBr. Again, oxygen needs protonation. Come to tap the hydrogen, kicks off on the bromine. All right. And I get my oxygen with a CH3 plus charge. Again, my bromine that is negatively charged comes in, attacks my carbon. It has no choice because we haven't learned anything about the addition of benzene ring yet. Right? And then these bonds break on the oxygen. And again, this is what we form. We actually form phenol and methyl bromide. All right. So again, these are, and again, remember we said that the reaction stops here. So again, these are the mechanisms of ethers, essentially. Nothing too serious, nothing complicated. But just remember, ethers do not react in basic conditions. So if I were to take this molecule here and add maybe say sodium hydroxide, here's what I would get. No reaction. All right. And some people like to think of it as, oh, let's see. Okay, well, we have sodium. So my OH is going to act as my nucleophile. My OH attacks, kicks off on the oxygen, and I form this plus an OHS bond. Right? And this is just simply not correct. Right? That's wrong. Ethers do not react in base. Typically, ethers react in acidic conditions. So just remember and keep that kind of leveled in your head for me.